Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper for exam for February-March 2019. So let's get started. Question 1a says define acceleration, that would be the rate of change of velocity. Part B says figure 1.1 shows the distance time graph for a journey of a cyclist. We have the distance on the y-axis and the time on the x-axis. Part I says describe the motion of the cyclist in the time between 0 and 15, then 15 and 30, then 30 and 40. In the graph we have the gradient increasing between 0 and 15 seconds, and then there is a straight line from 15 to 30, and then a decreasing gradient from 30 to 40. And the gradient is equal to the velocity, so increasing gradient is increasing speed or accelerating, constant gradient is constant speed, and then decreasing gradient is decreasing speed or decelerating. So that's what we are going to write here. First accelerating, then constant speed, and lastly decelerating or decreasing speed. Part I says calculate for the 40-second journey the average speed, and the average speed is equal to the total distance divided by the total time. On the graph we have the total distance to the end of the journey is 300 meters and the total time is 40 seconds. So we divide 300 by 40. That gives an answer of 7.5 meters per second. And part 2 says calculate the maximum speed, which we can get from the gradient of the graph. The part with the maximum gradient is between 15 seconds and 30 seconds, and we can use these points as the coordinates for a gradient. So y2 is 250, y1 is 70, and x1 is 15, x2 is 30. First we mention the equation that the speed is equal to the gradient, and then we substitute. We have 250 minus 70 divided by 30 minus 15. That gives an answer of 12 meters per second. Question 2a says state one advantage and one disadvantage of using a wind turbine as a source of electrical energy. We can say that for an advantage that it is non-polluting, or it is clean source of energy, or we can say that it is a renewable source of energy. As for the advantage, we can say that it is expensive or has initial cost that is high or high initial cost, and it also causes sound pollution and can endanger wildlife or bird life. Part B says figure 2.1 shows a wind turbine. Part I says the wind blows at a speed of 16 meters per second towards the turbine blades. In 1 second, a volume of 24,000 meter cubed of air passes through the circular area swept out by the blades. The density of air is 1.3 kilograms per meter cubed. Calculate first the mass of air that passes through the circular area swept out by the blades in 1 second. So we can say that the mass is equal to density multiplied by volume, and we have the density 1.3 and the volume 24,000, and the units here are the same, and the unit for the mass in density is kilograms, so we have the final unit is kilograms. This gives an answer of 31,200, or we can say that it is approximately 31,000 kilograms. Part 2 says the kinetic energy of the mass of air that passes through the area swept out by the blades. We can calculate the kinetic energy as half times the mass multiplied by the speed squared. We already calculated the mass, but we use the real value 31,200 by the speed, which was 16, and then we have the square. This gives an answer of 3,993,600, which we can approximate to 4 million or 4.0 times 10 to the power of 6, and the unit for energy is joules. I says suggest why some of the kinetic energy of the air that passes through the circular area swept out by the blades is not converted into electrical energy. One of the reasons is that not all the air passing actually hits the blades, or we can say that there is some energy lost as heat due to friction inside the mechanism of the system or the turbine itself, or we can say that air does not completely stop when it hits the blades, so not all the kinetic energy is converted to electric energy. Question 3a says an object is moving in a straight line at constant speed. State 3 ways in which a force may change the motion of the object. So the motion can either change as an acceleration or deceleration or changing direction. So we can say increase in speed or decrease in speed or change in direction. These are the options for changing the motion. Part B says figure 3.1 shows an object suspended from two ropes. The weight of the object is 360 newtons. The magnitude of the tension in each rope is T, which is unknown, but is at an angle of 45 degrees to the horizontal. In the space below, determine the tension T by drawing a vector diagram of the forces acting on the object and state the scale you have used. So we can measure the distance of the empty space here. We can get the ruler and measure the vertical distance between the wording of the question and the space for the answers. That's approximately 7 centimeters. And we have the magnitude of the vertical force here, 360 newtons. So 36 is close to 6. So if we multiply 6 by 6, we get actually 36. So we can say that we are going to draw the 360 newtons as 6 centimeters. So if we say that 360 newtons is equal to 6 centimeters, the scale would be how many newtons for 1 centimeter? So we divide 360 by 6, so that would be 60 newtons. So 1 centimeter is equal to 60 newtons. That is the scale. And for the shape of the forces, we have 360 must be equal to the resultant of the two tensions upwards. So this is 360 newtons. So if we draw the tensions as head to tail addition, so the first tension is pointing like this, the next one is pointing like this, and the resultant must be vertical and equal to 360. This angle here is 45 degrees and the angle from the horizontal here is 45 degrees. And this is also 45 degrees as an alternating angle to this. If we take the right angled triangle in the upper section, if this is 45 and this is 90, then this must also be 45. So we are left by the triangle shape of 360 vertical on this side and two tensions with angles 45 degrees from the vertical line. So we are going to draw it like this. So we have 360 here, tension here, and tension here, T and T, with angles 45 degrees from the top and from the bottom to the right of the 360 Newton force. We start by the vertical force, which is 360, and we draw a line 6 centimeters long to represent the 360 newtons. Then we use a protractor to measure 45 degrees from the top and the bottom, but we place the center of the protractor at the edges and make sure the base of the protractor is at the right angle with the line we've drawn, and mark 45 degrees from the top. Then we do the same at the bottom and we label the 45 degrees here. Now we connect the lines. From the top, we use the mark we've made and we draw a long line because we do not know where the line ends. We do the same for the other force from the bottom of the 360 Newton arrow. And again, we connect the mark for the angle and we draw a long line. So the intersection is actually the end point of the line, and these are just extensions or additions to the lines. So the vector diagram looks like this. And this is the 360 Newton force. This is the first tension and this is the second tension. And these angles are 45 degrees at the bottom and at the top. Now we measure the distance of each of the T lines. For my diagram, this is approximately 42 centimeters. So I'm going to multiply the distance 4.2 times 60. That was 4.2, not 42. That gives an answer of 252 newtons. And by the way, not all of you will get the same exact diagram, so not the same exact final result for the tension force. Question 4 is about barometers, so you can skip this question for the new syllabus. Part A says figure 4.1 shows a mercury barometer. The tube containing the mercury is vertical. The height h indicates a value for the atmospheric pressure. State what is contained in the space labeled S above the mercury in the tube. That would be nothing, or we can say that it is a vacuum or no molecules. Double I says on a particular day the atmospheric pressure is 1.02 times 10 to the power of 5 Pascal. The density of the mercury is 13,600 kilograms per meter cubed. Calculate the value for H indicated by the barometer. We use the equation pressure equals rho GH, and then we substitute 1.02 times 10 to the power of 5 is equal to the density 13,600 multiplied by 9.8, then multiplied by the H. Then we divide the left hand side by this bracket to get H, which will be equal to 0.7653, and we can approximate that to 0.76, and the unit here is in meters. Triple I says the tube containing mercury is now tilted so that it makes an angle of 10 degrees with the vertical. After tilting, there continues to be a space above the mercury in the tube. State and explain whether the vertical height of the mercury in the tube is smaller, the same, or greater than the value calculated in AII. We say that it will be the same or same value since the pressure affects the vertical height, not the incline, and atmospheric pressure did not change. So the height will not change. Part B says another mercury barometer in the same room at the same time shows a lower value of H than barometer in A. So it is in the same room. This means that it is the same atmospheric pressure, so no change in atmospheric pressure. There can only be one meaning that something is pushing down on the liquid in the tube. That would be something inside the area S. For example, some air bubbles escaped inside the tube and entered the area S and are now pushing down on the mercury in the tube. So we can say there could be some air in S or above the mercury in the tube. Question 5 is about thermometers, which was removed from the syllabus, so you can skip this question as well. Part A says state the values of the fixed points of a temperature scale. That would be 0 degrees Celsius and 100 degrees Celsius. Part BI says the graduation on a liquid in glass thermometer are equally spaced. For the equal spacing of the graduation to be correct, state an assumption that is made about the liquid in the thermometer. That would be linearity, or that it expands linearly with temperature. And the assumption that is made about the structure of a thermometer, that would be a constant cross-sectional area. Part I says liquid in glass thermometer A has greater range than liquid in glass thermometer B. State one way the design of thermometer A is different from thermometer B. The only way to increase the range is by increasing the length. So we can say that A is longer than B. I says liquid in glass thermometer C has a greater sensitivity than liquid in glass thermometer D. State one way the design of thermometer C is different from thermometer D. We can say that C has a larger bulb or thinner tube or capillary tube. These affect the sensitivity. Part CI says in the space provided, draw a label diagram of a thermocouple thermometer. It is made of a voltmeter with two wires coming out of the voltmeter, and these wires must be made of the same metal, and the edges of the wires are connected with a third wire that is made from a different metal. One of the meeting points is called a hot junction, the other is called a cold junction. The cold junction is placed in pure melting ice, so we draw something like this and we label it pure melting ice, or we label it 0 degrees Celsius, and then we label two of the wires coming from the voltmeter with metal 1, for example, or give an example of a metal like copper or iron, and for the third wire we say metal 2, or we choose another metal other than one we chose for the wires of the voltmeter. CII says suggest when a thermocouple thermometer is more suitable than a liquid and glass thermometer. We can say we use it for measuring rapidly changing temperatures, or we can say we use it for a wide range of temperatures. It can measure a wide range of temperatures, from very low temperatures to very high temperatures, going to the melting points of metals. So these are the advantages of a thermocouple. Question 6 says an electrical heater is placed on the floor of a room in a house. The heater is switched on. Part A says state the main process by which thermal energy is transferred to the air in all parts of the room. That would be convection, since we are talking about a fluid. Part B says the heater has a power of 1.5 kilowatts. The air in the room has a mass of 65 kilograms. The specific heat capacity of the air is 720 joules per kilogram degrees Celsius. I says calculate the time it takes for the heater to raise the temperature of the air in the room from 8 degrees Celsius to 15 degrees Celsius. We can say that energy is equal to mc delta T, or power multiplied by time is equal to mc delta T. So we have the power of the heater, 1.5 times 10 to the power of 3 to convert kilo, multiplied by the unknown time is equal to the mass, 65 kilograms, multiplied by 720, the specific heat capacity, and the change in temperature, 15 minus 8. And then we divide by 1500 on the right side to get a time of 218.4 seconds, which is approximately 220 seconds to two significant figures. I says state two reasons why the time calculated in BI is smaller than the actual time taken to raise the temperature of the air in the room from 8 degrees Celsius to 15 degrees Celsius. We can talk about two ideas about heat losses. We say that the heater also heats the walls, floors, and ceiling of the room. Or we can say that heat conduction through walls and windows to the surroundings is one of the reasons we lose heat. Question 7a says in figure 7.1, the small circles represent molecules. The arrows refer to the change of state from the arrangement of molecules on the left to the arrangement of molecules on the right. So we have in X a regular arrangement into an irregular arrangement, but the spaces between molecules are still close or small. In Y, we have from an irregular arrangement to another irregular arrangement, but the spaces increased dramatically. So from X, here we have a change of solid to liquid, and for Y we have a change from liquid to gas. Part B says explain in terms of the forces between their molecules why gases expand more than solids when they undergo the same rise in temperature. We can say that the intermolecular forces in solids are much stronger than in gases, so gas molecules are easier to separate since the attraction between them is less. Question C says a cylinder of volume 0.012 meter cubed contains a compressed gas at a pressure of 1.8 times 10 to the power of 6 Pascal. A valve is opened and all the compressed gas escapes from the cylinder into the atmosphere, and the temperature of the gas does not change. Calculate the volume that the escaped gas occupies at the atmospheric pressure of 1.0 times 10 to the power of 5 Pascal. First, we can use the equation P1V1 is equal to P2V2 and substitute. We have 1.8 times 10 to the power of 6 multiplied by 0.012 is equal to the new pressure 1.0 times 10 to the power of 5 multiplied by the new volume V2. And then we can get V2 by dividing the left-hand side by 1 times 10 to the power of 5. That gives a volume of 0.216 meter cubed. But that is the volume of the escaped gas and the gas still inside the cylinder. To get the volume of the escaped gas alone, we subtract the total volume of the final gas and the one that is still inside the cylinder, which has the volume of the cylinder 0.012 meter cubed. That gives an answer of 0.21 meter cubed. Question 8 says figure 8.1 shows parallel wavefronts of a light wave in ice. The wavefronts are incident on a boundary with air. So going from ice to air, that means that the light speeds up. And it says the speed of light wave in air is 3.0 times 10 to the power of 8 meter per second. The refractive index on the ice. The refractive index of the ice is 1.3. On figure 8.1, first draw the wavefronts of the wave that passes into the air, then draw arrows to show the direction of travel of the refracted wave, and label the angle of incidence I and angle of refraction R. So for the drawing here, we have an arrow representing the direction before the boundary. We can continue this line until it hits the boundary between ice and air. And then from this point, we draw a normal. And we must make sure that the normal is perpendicular to the boundary between the two media. So the angle between the normal and the boundary must be 90 degrees. You must measure it using a protractor. And then we draw the normal as dashed lines like this, just to represent that is not a ray of light. And then going towards a medium with higher speed for the wave, that means we are going to bend away from the normal. So we should have continued in this direction, but we go away from the normal like this. So this is the new direction of the wave. This is one of the required parts of the question. And then we draw the wavefronts perpendicular to the new direction from the intersection with the boundary. So like this, we started from this point where the wavefront hit the boundary and we drew 90 degrees on this line on the direction of the new wave. After that, we draw parallel lines to the new wavefront like this from the intersection points of the other wavefronts. We just have to make sure that they look equally spaced and parallel to each other to say that the speed of the wave in air is all the same, but the wavelength is longer in air than it was in the ice. Now for the angle of incidence and refraction, it is the angle between the direction of the wave and the normal before the boundary, that is incidence, and the angle between the direction of the wave and the normal after the boundary, that is the angle of refraction R. Part B says calculate the speed of light wave in the ice. We have the equation for refractive index is equal to the speed in air divided by the speed in the medium. So 1.3 is equal to 3.0 times 10 to the power of 8 divided by the unknown speed. We replace these two. So the speed of the wave in ice is equal to 3 times 10 to the power of 8 over 1.3. That gives an answer of approximately 2.3 times 10 to the power of 8 meters per second. Question 9 says figure 9.1 shows current potential difference graphs for a resistor and for a thermistor. Calculate the resistance of the thermistor when the potential difference across it is 7 volts. We need the current of the thermistor. So at 7 volts here, we go to the graph and then we show the current on the y-axis. This current is approximately, actually it is 4.6 amperes. So we use the equation resistance is equal to V over I, or voltage over current. So 7.0 divided by 4.6, that gives an answer of 1.521739, which we can approximate to 1.5 ohms. Part B says in table 9.1, tick the boxes that indicate the effect on the resistance of the resistor and the thermistor when potential difference across them is increased from 0 to 7 volts. So the resistance is represented by the slope of the graph, and since the resistance is equal to voltage over current, then the further away you get from the voltage axis, that means the resistance decreases. The closer you get to the voltage axis, resistance increases. But for the resistor, that is a straight line. It does not get closer or away from the voltage axis. It has the same gradient. So for the resistance does not change. As for the thermistor, it moves away from the voltage axis. That means that the resistance decreases. So for the resistor, resistance is constant, and for the thermistor, resistance decreases. Part C said the thermistor and resistor are now connected in parallel to a 7 volt supply, and in the graph the lines intersected at 7 volts, so they both had 4.6 amperes as current, but they are connected in parallel, so the resistor had current 4.6 amperes and the thermistor also had current 4.6 amperes, but in parallel these currents will add up to get the total current. First, it is required to calculate the total current of the supply, so it is the total of these two currents, or 4.6 plus 4.6, or we can multiply 4.6 times 2. That gives an answer of 9.2 amperes. Double I says the energy transferred from the supply in 5 minutes is required. We already calculated the current, or we have the current in each one of them, and we have the potential difference, or we have the total current and the potential difference. We can use energy is equal to VIT. If we need the supply power or energy, we use the total voltage and total current. So the total voltage is 7, total current is 9.2, and the time cannot be left in minutes, it must be converted to seconds. So we multiply by 60. That gives an answer of 19,320, which is approximately, to two significant figures, 19,000 or 1.9 times 10 to the power of 4 joules. Question 10a says the electrical energy produced by a power station is transmitted over long distances at a very high voltage. Explain why a very high voltage is used. That is the concept of stepping up the voltage to decrease the energy losses, but that happens because when voltage is stepped up, the current decreases. This reduces heat losses in the cables, but that only gives us 2 marks. We need another mark, so we say, and there is no need for thick wires to decrease resistance, because power loss is equal to the current squared multiplied by the resistance. If we've already decreased the current, there is no need to decrease the resistance to decrease the power losses. Part B says figure 10.1 represents a transformer. We have the primary coil P has 4000 turns and an input of 120 volts. So this is NP and VP. The secondary coil S has an output voltage of 9 volts. This is VS. Calculate the number of turns in the secondary coil. We can use NS over NP is equal to VS over VP, and then substitute. NS is unknown, NP is 4000 turns, VS is 9, VP is 120 volts, and then we cross multiply 4000 times 9, and then we divide by 120. That gives an answer of 300 turns. Double I says state a suitable material for the core of the transformer. It must be a soft magnetic material to get magnetized and demagnetized with the changing magnetic field of the alternating current. So we use iron or soft iron. Question 11AI says one isotope of iridium 194 is represented by IR 194 and 77. This isotope decays by beta emission to a stable isotope of platinum. Complete the nuclide equation for this decay. First, we must memorize the numbers for beta, which are 0 and -1. And we memorize that for beta decay, the nuclear number does not change, so it is still 194. And the proton number increases by 1. It will be 78. So that 78 minus 1 is equal to the 77 on the left-hand side of the arrow. Double I says the half-life of iridium 194 is 19 hours. A sample of iridium 194 has an initial count rate of 1100 counts per minute. So this is the initial activity. Calculate the count rate from this sample after 38 hours. This is the total time, and we have the half-life, and the required is the final activity. So if we have the half-life and total time, we divide the total time 38 by the half-life to get the number of half-lives. That gives us 2 half-lives, which means we will divide by 2 times. So starting from 1100, dividing that by 2, that gives us 550. Dividing that by 2 another time for the second half-life, that gives us 275 counts. And this is the final answer. So we write 275 counts per minute using the same unit as the questions unit. Part B says state 2 ways in which gamma emission differs from beta emissions. We can say gamma has no charge and beta is negatively charged, or we can compare speeds and masses. Gamma has no mass and beta moves with a very high speed, close to the speed of light. Or we can say that gamma is an electromagnetic wave and beta is an electron, which is the nature of the radiation. So this was the end of the exam. I hope you enjoyed this video and found it useful. If you like this video, give it a thumbs up and subscribe to the channel, and I will see you in another video.